NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will prove that the roots of the quadratic equation open parenthesis, a plus b close parenthesis x squared minus open parenthesis, a plus b plus c close parenthesis x plus c over 2 equals 0 are always real. We will do this by showing the discriminant is always non-negative. First, we will identify a, b, and c. The condition for real roots is that the discriminant delta is greater than or equal to 0. The discriminant is b squared minus 4ac. Now substitute a equals a plus b equals negative open parenthesis, a plus b plus c close parenthesis, and c equals c over 2. We simplify each part. The square of negative open parenthesis, a plus b plus c close parenthesis, is open parenthesis, a plus b plus c close parenthesis squared. Next, for times, a times c becomes 2c times open parenthesis, a plus b close parenthesis. Putting this together gives the simplified discriminant. Now, expand the trinomial square and distribute. The square of a plus b plus c equals a squared plus b squared plus c squared plus 2, ab plus 2, ac plus 2bc. The quantity 2c times a plus b equals 2, ac plus 2bc. Substitute these into the discriminant and combine like terms. We see plus 2 ac minus 2 ac cancels, and plus 2 bc minus 2bc cancels. Now group the first, second, and cross term to form a perfect square. We can write delta equals open parenthesis, a plus b close parenthesis squared plus c squared. To build intuition, think of these as areas of two squares, one with side a plus b and one with side c. Areas are never negative, so their sum is non-negative. Since squares of real numbers are always non-negative, delta is greater than or equal to 0 for all real a, b, and c. If a plus b equals 0, the equation is linear or identically 0, which still has real solutions. Therefore, the roots are always real. In this lesson, we will prove that the quadratic equation x squared minus 2ax plus 3a squared plus b squared equals 0 has no real roots. We will use the discriminant test and also confirm the result by completing the square. Strategy 1. Use the discriminant. A quadratic ax squared plus bx plus c equals 0 has no real roots if and only if its discriminant delta is less than 0. Here a equals 1, b equals negative 2a, and c equals 3a squared plus b squared. We compute delta equals b squared minus 4ac. Substitute b equals negative 2a, a equals 1, and c equals 3a squared plus b squared. Then expand and simplify carefully. Negative 2 a quantity squared gives 4 squared. Next, subtract 4 times 1 times the quantity 3 a squared plus b squared, which is 12 a squared plus 4b squared. Combining like terms gives negative 8 a squared minus 4b squared. Factor out negative 4 to get negative 4 times the quantity 2 a squared plus b squared. Now, interpret the sign of delta. Both a squared and b squared are greater than or equal to 0. Therefore, the quantity 2 a squared plus b squared is non-negative, and it is strictly positive unless a and b are both 0. Multiplying a non-negative number by negative 4 gives a number less than or equal to 0, and strictly less than 0 unless it equals 0 and b equals 0. So, for any values where a and b are not both 0, the discriminant is negative, which means the quadratic has no real roots. Let us address the special edge case when it equals 0 and b equals 0. Then the quadratic becomes x squared equals 0, which has a real repeated root at x equals 0. Apart from this degenerate case, the equation has no real roots. For deeper intuition, complete the square. X squared minus 2, ax plus 3 a squared plus b squared can be rewritten as the square of x minus a plus the constant 2 a squared plus b squared. This is a vertical parabola whose vertex is at x equals a, with a minimum y value of 2 a squared plus b squared. Since that minimum is positive unless it equals 0 and b equals 0, the graph does not cross the x-axis, which confirms there are no real roots in the general case. Final conclusion. For all real a and b not both 0, the discriminant is negative, so the quadratic has no real roots. The only exception is it equals 0 and b equals 0, giving x squared equals 0 with a repeated real root at 0. In this example, we will prove that the equation 1 over x minus a plus 1 over x minus b equals 1 over c squared always has real roots. We'll convert the equation into a standard quadratic, and then show that its discriminant is always non-negative. Step 1. Combine the fractions on the left side by using a common denominator. The common denominator is x minus a times x minus b. Now simplify. The numerator becomes 2x minus a minus b. The denominator expands to x squared, minus the quantity a plus b, times x plus ab. Next, clear the fractions by cross-multiplying. Multiply both sides by c squared times the denominator, x squared minus the quantity a plus b times x plus ab. Distribute c squared on the right side. Now move all terms to the left side to form a standard quadratic equal to 0. Then group the x terms together and the constants together. Now identify the coefficients. A equals 1, b equals negative, a plus b plus 2c squared. A equals 1, b equals negative, a plus b plus 2c squared. C equals ac squared plus bc squared plus ab. For a real root, the discriminant, delta, must be greater than or equal to 0. Delta equals b squared minus 4ac. Substitute a, b, and c into the discriminant inequality. Now expand the square and the product terms. Then simplify by canceling like terms. Finally, combine the remaining terms. Now recognize a perfect square in the first 3 terms. A squared minus 2ab plus b squared is the same as the quantity a minus b squared. Therefore, the discriminant simplifies to the quantity a minus b squared plus 4c to the 4th, which is always at least 0. That means the equation always has real roots. Equation always has real roots. In this example, we will find the domain of the expression p equals the square root of 1 over x squared minus 3/4. We will proceed step by step using rules for square roots and rational inequalities. Step 1. For any square root, the argument must be greater than or equal to 0. Also, because we have 1 over x squared, x cannot be 0. Let us write the inequality for the radicand being non-negative. Then we will note x not equal to 0. Step 2. Combine the fractions into a single rational expression using a common denominator of 4x squared. Now, we write the combined form. Step 3. Find the roots of the numerator for minus 3x squared. Set it equal to 0 and solve for x. These roots make the entire fraction equal to 0, and they are included in the domain because the inequality is greater than or equal to 0. Step 4. Equal to 0. Step 4. Now find the roots of the denominator 4x squared. Setting 4x squared equal to 0 gives x equals 0 a double root. This point must be excluded because the denominator cannot be 0, and a double root does not change the sign across that point. Step 5. Use a number line to analyze signs. The critical points are negative 2 over root 3, 0, and positive 2 over root 3. The numerator 4 minus 3x squared is positive between its roots and negative outside. The denominator 4x squared is positive everywhere except 0, where it is 0 and undefined for the fraction. Therefore, the fraction is non-negative on the intervals inside the roots, excluding 0. In this example, we will solve a rational inequality that models weekly sales. The sales function is given by s of t equals 200t divided by t squared plus 100. We want the time period when weekly sales are at least 8,000 units per week. First, build intuition with a graph. We plot s of t against time in weeks. Then we draw the horizontal line, s equals 8. Notice the intersections at t equals 5 and t equals 20. Between these times, the curve is at or above 8. Now solve it algebraically. We want s of t greater than or equal to 8. Substitute the formula for s of t. To solve a rational inequality, bring all terms to one side and compare to 0. Use a common denominator to combine into a single fraction. Distribute the negative 8 and simplify the numerator. Set the numerator equal to 0 to find critical points. Factor out negative 8 and factor the quadratic. Solve for t. Check the denominator. Since t squared plus 100 is always positive for real t, the sign of the fraction is controlled by the numerator only. Perform a sign analysis using the roots 5 and 20. Check the denominator. Since t squared plus 100 is always positive for real t, the sign of the fraction is controlled by the numerator only. Perform a sign analysis using the roots 5 and 20. The quadratic opens downward, so it is non-negative between the roots and negative outside. Therefore, the solution is t between 5 and 20 inclusive. Final answer. The weekly sales are at least 8,000 units per week for all times t in the closed interval from 5 to 20 weeks. In this example, we compare two projectile heights and solve a quadratic inequality. The function h of t equals negative t squared plus 10t gives Jack's ball height in meters. The function g of t equals negative 3t squared plus 18t gives Jonathan's ball height in meters. We want the times when Jonathan's ball is higher than Jack's ball. Let's visualize both heights on the same axis. The horizontal axis is time in seconds, and the vertical axis is height in meters. We plot h of t in orange and g of t in blue. Notice they intersect at t equals 0 and t equals 4. We want the times when Jonathan is higher than Jack. That is, g of t is greater than h of t. Substitute the functions. Move all terms to one side and combine like terms. To solve the inequality, first find the boundary points by setting the expression equal to 0. Factor out common terms. This yields the critical times t equals 0 and t equals 4. The parabola opens downward, so the expression is positive between the roots. That means g of t is greater than h of t, downward, so the expression is positive between the roots. That means g of t is greater than h of t for t between 0 and 4 seconds. Visually, we can shade the region between the two curves from t equals 0 to t equals 4. Intuition check. 2 soccer balls are kicked, and for the first 4 seconds, Jonathan's ball stays higher than Jack's ball before they cross again. Final result. Jonathan's ball is higher when t is in the open interval from 0 to 4 seconds. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.